Chugging along over here, what is the magnitude of the net force required to accelerate a 1,200 kilogram car uniformly from 0 meters per second to 27 meters per second in 10 seconds? Newton's second law tells us that F equals ma. We're given m over here. So in order to find F, we just need to find A, which we're going to use using this information over here. This over here is our VI, this over here is our VF, and this over here is our T. VF equals VI plus AT. So 27 equals 0 plus A times 10, which is just A ends up equaling 2.7. Therefore, F equals 1,200 times 2.7, which, as you can see over here, is 3,240. A block lies on a horizontal frictionless surface. A horizontal force of 100 newtons is applied to the block to give rise to an acceleration of 3 meters per second. Determine the mass of the block. Calculate the distance the block will travel with forces applied for 10 seconds, etc., etc., etc. So, F equals ma. If you apply a force of 100 newtons, that results in an acceleration of 3 meters per second. The mass is just going to be 100 divided by 3, which is 33.33 kg. That's the answer to part A. Calculate the distance the block will travel with the forces applied for 10 seconds. So we're looking for distance, which is delta x. We're given a time, which is 10. The block is lying on the horizontal surface, so that means that our VI equals 0 because it's not initially moving before there's a force. So we have VI, we have T, we're looking for delta x, and we have A, which is 3. So delta x equals VIT plus 1/2 AT squared. VI is 0, so this goes away, so it's just 1/2 times 3 times t squared, which is 100, and we get 150 as our answer. So delta x equals 150. That's how far it travels. The speed of the block is VF. So now we're solving for VF. VF equals VI, which is 0, plus A, which is 3, times T, which is 10. VF equals 0 plus 3 times 10, which is 30 meters per second, and that is the answer. 50 kilogram box is being pulled along a horizontal smooth frictionless surface. The pulling force is 25 newtons directed at an angle of 12 degrees above the horizontal. What is the normal force on the floor pushing the box? What is the magnitude of the acceleration of the box? Let's draw a free body diagram. The weight of the box is pushing down, and the normal force is pushing up, and we have this force right over here, the applied force, magnitude of 25, angle of 12. In order to calculate the normal force, we need to realize that the box is moving along the horizontal smooth surface, which means it's not going up or down, which means that AY equals 0, which means we have equilibrium in the y direction. The net forces, F net equals F net in the y direction equals MAY. AY equals 0, which means the net force in the y direction needs to equal 0, which means, in other words, all of our up arrows need to equal all of our down arrows. So we have one down arrow, which is the weight, equals the mass of the box times 9.8. We can calculate it pretty easily as 50 times 9.8, which is 490. We have two up arrows. We have N, which is what we're solving for, and we have the Y component of this force over here, which we can calculate pretty easily because it's opposite. So it's going to be sine of 12 times 25, and it's 5.2. So N plus 5.2 needs to equal 490, which makes it pretty easy to see that N equals 484.8, because 490 minus 5.2, 44.8. What is the magnitude of the acceleration on the box? So since all of the up arrows and all the down arrows cancel out, your only thing you're left with is this sideways arrow over here, which is the x component. So the net force is just going to be 25 times cosine of 12. It's going to be that guy over there. That is the net force. F equals ma. So we're going to divide by the mass in order to find the acceleration. Divide by 50, we get 4.9.49 is our acceleration, meters per second squared. That is our A. Only two forces act on a 40 kilogram object. One is a magnitude of 60 newtons and it's directed 34 degrees. So this is force A. It's directed 34 degrees south of east. This is east, this is 34 degrees to the south. X component, Y component. Second force is directed north of west, 40 degrees north of west. This is west, this is to the north of it. X, Y, blah, blah. So this is 60 newtons, this is 35 newtons. So let's draw a free body diagram on the object. So blah, blah, blah. That's the free body diagram. There are only two forces. There are only two ones that we care about. Fine. The x and y components of the object's acceleration. So in order to find ax, we need the f net in the x direction, because f net x equals max, and f net y equals may. So the net force in the x direction is this x component plus this x component. This x component over here is 60 cosine 34. This x component over here is 35 cosine 40. This guy's positive, this guy's negative, so we're going to do 49.7 minus 26.8. That is the net force. We're going to divide by the mass to find ax. So that guy over there, answer divided by 40, gives us an ax. It gives us an ax of 0.573. For the y's, we're going to do the same thing with sine. So this guy is 60 sine 34, and it's negative. This guy is negative. The other one's going to be 35 sine 40, and it's going to be positive. So it's the answer. Oh, go away. Sine 40. So it's going to be the answer minus 33.55. AY ends up being negative. Wait. Oh, sorry. That's F. That's F net Y. Hang on. Let's rewrite that. So AX was 0.573. So F net Y ends up being negative 11.5. We're going to solve for AY by dividing by the mass. Answer divided by the mass gives us an AY of negative 0.276. The magnitude and direction of the object's acceleration we're going to find by using the Pythagorean theorem. We're going to take the square root of the answer squared, and we're going to add 0.573 squared, and we're going to get a magnitude of 0.64, and a direction we're going to get by doing an inverse tan function. We're going to do 0.276 divided by 0.636, and we get an angle of 23 degrees. Negative A, negative Y, positive X. So we're going south and to the right, which is southeast. So 23 degrees southeast, south of east or southeast. Traffic light weighs 100 newtons and is supported by two ropes shown in the figure. So this angle is the same as these angles over here. These angles are the same, which means that the tensions in each cable is going to be the same. In order to find the tensions, we need to recognize that this is an equilibrium problem, which means that the down arrow has to equal the two up arrows. So Ty plus Ty has to equal the weight. The weight is given to us explicitly as just 100. We don't even need to multiply the mass because they don't give us the mass, they just give us the weight. So Ty plus Ty needs to equal 100, which means that Ty equals 50. If Ty equals 50, and this angle over here is 37, we can solve for t by seeing that sine of 37 equals 50 over t, which means that t equals 50 divided by sine of 37. 50 divided by the sine of 37 is, sine of 37 is 83. The tension is 83. The puck slides a total of, oh, this is awkward. I changed this to the 2 kilogram puck slides a total of 8 meters on a horizontal surface before coming to a rest. If the coefficient of kinetic friction between the puck and the board is 0.2, what is the initial speed of the puck? So we're given a coefficient of friction. We can use that in conjunction with the normal force to find the force of friction. We can use the force of friction to find the acceleration. And then we can then use the acceleration to solve this particular kinematic equation, because we're given a delta x and we're given a vf, so we can solve for a vi if we know what a is. So we're going to use the coefficient with the normal force to find the force of friction. We're going to use the force of friction to find the acceleration, and then we're going to find acceleration to find vi. So let's draw a free body diagram. The puck is weighed down, it has a normal force pushing up, and the friction is just slowing it down. So that is the force of friction over here. The force of friction equals the coefficient of kinetic friction, which we're given, times the normal force. Since there are no other up or down arrows in this particular question, the normal force is equal and opposite to the weight, which equals the mass times acceleration due to gravity, which is 19.6. And the coefficient of friction is 0.2, which means that the force of friction in this particular problem is 19.6 times 0.2. So the force of friction is 3.92. That's also going to be the net force, because again, the up and down arrows cancel out. So the net force is just this over here, 3.92, which means F equals MA. 3.92 equals the mass, which is 2 times A, divide both sides by 2. Answer divided by 2 gives us an A of 1.96. Back to the kinematic question. So now we know A, we know VF, we know delta X, and we're looking for VI. So VF squared equals VI squared plus 2A delta X. 0 squared equals VI squared plus 2 times 1.96 times 8. 2 times 1.96 times 8. We're going to subtract 31.36 from both sides and take the square root. Sorry, I made a mistake over here. This a needs to be negative, because otherwise I'd end up taking the square root of a negative number. The reason why this a is negative is because the puck is being slowed down, aka this is a negative force, because it's to the left, it's slowing down the puck. So therefore, the force is negative and a is negative, which means that this is negative 1.96, which means when we subtract it, we end up with a positive number. When we add it, we end up with a positive number, which means we're not taking the square root of a negative number. So none of that really mattered, because we're still just going to take the square root of this over here, and we're going to get VI as 5.6. An object is dragged with a force of 40 newtons directed 30 degrees above the horizontal. If the weight of the object is 29.4 N, and the coefficient of friction is 0.35, calculate the normal force acting on the object, that's N, the force of friction acting on the object, and the acceleration of the object. So again, this is another equilibrium problem. The object is dragged along the surface. It's not going up or down, which means, once again, our up arrows have to equal our down arrows. This up arrow over here is Fy. We can find it by taking the y component, which is 40 times sine of 30, which is 20, which means that 29.4 has to equal 20 plus n, which means n has to equal 9.4. If n equals 9.4, we can calculate the force of friction as the coefficient times 9.4. The coefficient is 0.35. So 9.4 times 0.35 is 3.29. So the force of friction is 3.29 newtons, which is going to allow us to calculate the net force. Again, our up arrows and our down arrows cancel out, so none of these matter. The only thing that matters is this right arrow over here, which is the x component, and the force of friction, which is going in the opposite direction. The x component is 40 cosine 30, and then we're going to subtract 3.29 to get a net force of 31.35. That net force is going to equal the mass times acceleration. 31.35 equals the mass times the acceleration. We're going to find the mass by taking the weight and dividing by 9.8, because this equals the mass times the acceleration due to gravity. So we're going to do 29.4 divided by 9.8, and we get exactly 3, which means the mass is 3, which means we could take 31.35 and divide by 3 to get A, which is 10.45, which is the acceleration of the object. An object slides along a level floor. It slows and comes to a complete stop with a constant acceleration of 3.1 meters per second squared. Was the coefficient of kinetic friction between the object and the floor? So it's sliding along a level floor. The weight is pulling down, the normal force is pushing up, those two cancel each other out, and the friction is just slowing it down. That force of friction, which we don't know, is the net force acting on the object, which means that we know that the force of friction is going to equal the object's mass times its acceleration, which we know is 3.1. We don't know the mass, but as we will see, we don't need to know the mass. The force of friction also equals the coefficient, which was what we're looking for, times the normal force. The normal force, since it's equal and opposite to the weight, which is always the mass times the acceleration due to gravity, we can rewrite this as the coefficient times the mass times 9.8. Since the force of friction equals the mass times the acceleration, which is 3.1, and it also equals the coefficient times the mass times 9.8, we can rewrite this as the mass times the acceleration equals the coefficient times the mass times 9.8. Since we have a mass on this side of the equation and a mass on this side of the equation, we could divide both sides by the mass, and the mass cancels out. That's why we didn't really need to know it, and we get that the acceleration equals the coefficient times g, or 3.1 equals the coefficient times 9.8, which means the coefficient is going to equal 3.1 divided by 9.8, which is 0.32, which is the answer. The coefficient is 0.32, and that is the end. This problem is just a repeat of an earlier problem, so I took it out.